Hi everyone, I'm Kaushik Ponnekanti. It's a pleasure to be here at the Conference 42 to share what I've learned about the quantum computing today. So, when I first began exploring this field, I vividly recall reading a paper that described quantum speedups as almost magical, science like fiction made real. I felt excitement mingled with skepticism. Of course, like who wouldn't, right? Could these fragile devices truly deliver the things that they are promising? Over time, small experiments convinced me there is substance beneath the hype. Today, we live in a NISC era where hardware remains imperfect but already offers tangible benefits in scoped problems. Over the next 20 to 30 minutes, I'll guide you through where we stand, why quantum matters, concrete examples in the industry, and how to prepare for what lies ahead. Let's begin by setting the scene and revisiting how we have arrived here and why even early experiments matter. So let's actually move on to where we stand today. What is the current quantum computing landscape? So, classical computing has driven incredible advances in smartphones, cloud services, machine learning, but certain challenges grow exponentially harder as scale increases. For example, the traveling salesman problem. Of course, who doesn't remember the traveling salesman problem? When you're reading about computer science, this is one of the most head scratching problems that one has read about, right? So, with a few cities, of course, it's trivial. Let's say, take an example of 2 to 3 cities, it's not as hard. But as you add more and more cities, possibilities literally explode. Or molecular simulations. Modeling electron interactions in even moderately sized molecules can quickly overwhelm because of the sheer number of electrons and, frankly speaking, how they interact with each other. Quantum computing introduces superposition and entanglement, letting us explore many possibilities in parallel and capture correlations beyond classical reach. So, which is exactly where we what we want. And in today's NISC hardware, we have tens to low hundreds of qubits, noisy operations, and limited coherence times. Despite these constraints, creative algorithms and hybrid workflows often yield advantages on scoped problems. Again, as I said, the problems need to be scoped. I remember a pilot where a small team simulated a simple molecule. Raw hardware results were very noisy, yet, after combining with classical approximations and error mitigation, they guided a chemist away from a costly lab test. Of course, we cannot afford to make expensive mistakes these days with so much technology available, and as such, these things matter. That success, even though felt modest, a fraction of a larger pipeline, but it actually built confidence and skills. Understanding this context prevents overhype. We pursue quantum even because even small wins now build expertise and position us for larger breakthroughs. Of course, this is exactly how industrial revolution started as well, right? So think of it like learning how you set to sail. You start with a small boat in a calm, open waters before you tackle the open ocean. Now, let's actually dive deep into the core quantum principles in practice. So, at the heart of the quantum advantage lies superposition and entanglement. So, again, like as you can see, basically there's a lot of jargon, and frankly speaking, it gets overwhelming when you're trying to learn new stuff. Of course, I can understand. So, let's take a simple example. Imagine spinning a coin. Until it lands, you don't know whether it is heads or tails. Similarly, a qubit can hold both possibilities simultaneously. When qubits entangle, their states link so that measuring one affects the whole, allowing representation of complex correlations classical bits cannot efficiently encode. So, in practice, algorithms like quantum approximation optimization evolved optimization objective into a circuit that samples candidate solutions. Though current devices are noisy, running shallow circuits and combining outputs with classical post processing can reveal better solutions than classical heuristics. I recall sitting in a meeting, right, like where engineers framed a logistics routing problem on a quantum test. So they took a region with about dozen stops, encoded cost functions into a variational circuit, and ran hardware experiments. Raw outputs were super noisy and inconsistent, but after collecting enough samples and applying mitigation techniques to mitigate the noise, they observed candidate routes that classical solvers could not even recognize. So they tested those routes in a simulation and saw slight improvements in total travel time. Again, I don't want to exaggerate the advantages that we got, because these are small wins that we are accounting for right now. It wasn't earth shattering, as I was just saying, but it demonstrated that quantum could contribute to something new. So again, it's a well-defined slice of a problem, as you can see. The variables are defined, the scope is defined, so on and so forth. That practical doorway, identifying a manageable piece that matters, is where NISC era value emerges. Because we want to definitely make sure that we are working with the classical computing, but again, we want to make sure that we do slightly better, even if possible. Now let's actually try to see how do we work with NISC constraints. What are the challenges that we are finding, and how do we navigate around it? So real hardware today isn't flawless. Noise corrupts calculations and qubit counts limit problem size. Instead of seeing this purely as a barrier, let's actually choose problems tailored to NISC machines. For example, small-scale portfolio optimization, simplified molecular models, or routing subproblems in logistics fit within tens of qubits and shallow circuits. Again, you don't want to go into hundreds of qubits because these are limited for now. Error mitigation techniques such as zero noise extrapolation or randomized compiling help extract meaningful results despite noise. I remember a team kind of running the same circuit at different gate durations to amplify noise and then extrapolating data back toward a zero noise estimate. Results aligned very close to the classical benchmarks than raw readings ever did. These steps require extra circuit runs. Of course, you want to make sure there are enough samples and basically and classical computation, but transforming noisy outputs into actionable insights. Hybrid workflows prove essential because this is where I think, again, we don't want to directly say either or that. So we want to use a hybrid approach. Classical pre-processing narrows candidate sets, and once you can narrow the candidate sets, quantum circuits refine or evaluate them. Classical post-processing interprets outputs to shortlist a few dozen, and then use quantum subroutines to estimate energies more precisely for that specific shortlist, guiding experimental decisions. In logistics, a global routing problem might be split into several regional slices. Classical solvers handle the broad layout, while quantum kind of pilots refine the specific legs for each of these constraints. So embracing constraints creatively is exactly what we are looking for. So now let's take a couple of examples, right? How do we handle quantum computing in the financial services landscape? In financial services, optimization and risk assessment draw very early interest because that is exactly what we look for whenever anybody speaks of financial services. Consider portfolio optimization. Classical solvers may take hours or days for large portfolios. A quantum-inspired ran mid-sized instances faster and suggested allocations that improved risk-adjusted returns modestly in pilot tests. Again, this is like purely pilot tests. In one case, a wealth management firm defined a pilot with 30 to 40 assets, integrating expected returns and covariance data. They ran various circuits on simulators and small hardware to sample candidate allocations and then compared them to classical solutions. The quantum-assisted results sometimes offered slight shifts that, when back-tested, showed a few basis points of improved Sharpe ratio. Those gains translate to a meaningful dollar value when assets under management scale into hundreds of millions. So another area is a Monte Carlo risk analysis. Classical Monte Carlo may require millions of samples to estimate tail risks. Quantum amplitude estimate promises reduced sampling requirements in ideal conditions. So while full speedups await more mature hardware, NISC-era hybrid sampling methods have cut simulation time modestly by integrating short-depth quantum circuits to estimate probabilities more efficiently. A risk team ran a pilot feeding random paths into quantum subroutine to assess extreme loss probabilities. While not a full speedup yet, it sharpened tail risk estimates in a fraction of classical-only pipeline time. Fraud detection also benefits. Encoding transaction address into quantum kernel methods can highlight subtle correlations classical methods usually miss. In a POC which was done, analysts coded features of transaction graphs onto quantum circuits and used outputs in a classifier. Result caught patterns that improved detection precision slightly. Again, as I said, small wins matter. These remains absolutely proof of concepts, but they teach teams how to integrate quantum subroutines, validate outputs, and align experiments with compliance and security needs. Organizations built this know-how, now that they are actually well prepared to where the hardware can scale and how to make sure we use hybrid approaches. Now let's take another example. What do we do in a pharmaceutical R&D case? So drug discovery and molecular simulation naturally align with quantum computing because that's where it's supposed to shine, right? Frankly speaking, chemistry obeys quantum mechanics and classical approximations struggle with electron interactions in complex molecules. Early experiments on small molecules like hydrogen chains, small organic compounds, demonstrate quantum circuits modeling electronic structure more faithfully. In one collaboration, researchers ran hardware experiments to estimate ground state energies of a small molecule. Raw results were very noisy, yet after mitigation and combining with classical methods, they matched expectations closely enough to filter out a false lead, which is very important and a huge win, frankly speaking. That saved weeks of lab synthesis and testing. In another example, completely different example, a virtual screening pipeline used quantum subroutines to define binding energy estimates for a shortlist of candidate ligands targeting a known enzyme. Classical docking produced 50 candidates. Quantum enhanced evaluation trimmed it down to 15. Experiment essays then prioritized the top 5, one of which showed promising activity. As you can see, the filtering is done very efficiently. Beyond small molecules, teams explore protein folding or binding site computations, while classical AI tools like AlphaFold excel at predicting structures. Quantum methods may offer complementary insights into energy landscapes or dynamic conformations. A startup ran hybrid loops. Classical simulation suggested several conformations. Quantum subroutines estimated relative energies under different conditions. Results informed lab experiments. In lead optimization, quantum enhanced machine learning refines predictions of toxicity or solubility. Encoding molecular descriptors into quantum kernel models sometimes improved classification accuracy on historical datasets, guiding selection of safer scaffolds. Pharma R&D also considers optimization of clinical trial designs, defining patient cohorts based on multiple biomarkers. Quantum-inspired algorithms help explore trial parameter spaces to maximize statistical power under budget constraints. A biotech firm ran a pilot to optimize trial arm allocations given limited patient populations and multiple endpoints. Of course, the results, while full-scale benefit awaits larger machines, the exercise built institutional understanding of mapping such problems to quantum-friendly formulations. These pilots show that investing in quantum chemistry and optimizational skills today speeds readiness for larger simulations when error-corrected machines arrive. Now, let's actually see how to do logistics and supply chain. Again, we are trying to establish how quantum computing can actually help in various industries, because of which it's better to go over each and how each of the POCs were done in each of the industries and understand better on how quantum computing can help. Logistical problems like vehicle routing, inventory allocation, and scheduling often become combinatorial mountains. In pilot studies, quantum inspired solvers explored routing variants beyond classical heuristics, uncovering alternate routes that reduce total distance or delivery time by a noticeable margin on scoped instances. For example, a delivery company modeled a region with 15 vehicles and 100 stops during peak season. Classical solvers found good solutions quickly, but a hybrid quantum test suggested a slight rerouting for one vehicle that literally avoided a traffic bottleneck predicted by recent data, shaving off 5% of the total time. Over hundreds of deliveries that quickly add up. Over lower labor costs, happier customers, essentially speaking. Inventory management benefits too. So now, optimizing stock across warehouses under capacity and demand uncertainties can use quantum enhanced heuristics. A retailer piloted a hybrid workflow where classical forecasts predicted demand distributions, quantum subroutines then optimized inventory allocations. The result reduced overstock by 10% and out of stock incidents by 8% compared to classical only benchmarks. So, scheduling maintenance crews across sites with various skills and time is another combinatorial challenge. A utility company tested quantum inspired servers to assign crews under multiple constraints. Early results showed 15% better utilization in simulated scenarios, prompting deeper investigation. Even demand forecasting sees quantum exploration. While classical machine learning dominates, some teams test quantum machine learning prototypes to capture complex feature correlations. In one pilot, a supply chain group encoded time series and categorical features into quantum feature maps and used variational classifiers to predict demand spikes. Accuracy improvements were modest but consistent across several data sets. The key is basically isolating manageable subproblems. Focus initially on critical product line or regional hub rather than the entire global network. It's important for us to slice the problem down into multiple smaller subslices. Now let's actually move on to how do we assess quantum hardware and simulators. Just a quick second. Yeah. So multiple platforms make quantum experiments accessible. Cloud services provide entry points to superconducting, trapped ion and annealing devices. AWS Bracket, Azure Quantum, IBM Quantum, Google Quantum AI all offer simulators with noise models and real hardware queues. When starting, prototype on simulars to refine circuits, check correctness, and anticipate noise impact. I recall juggling different SDK versions, one day testing on, then on Circ, then on an ion trap system via AWS. Each had its own quirks, frankly speaking. Documenting dependencies, gate sets, connectivity maps, and noise parameters became part of these workflows. So that upfront effort pays off. You already know how to adapt your circuits to newer devices. Queue times and costs vary, of course. Running many shots on real hardware can incur delay and expenses. To manage that, plan experiments carefully, simulate first, and then only run final circuits on hardware. Use noise-aware simulators to predict outcomes and catch major issues early. Keep experiments small. If a problem max to 60 qubits but device only offers 30 with good fidelity, identify a reduced instance or partition the problem into multiple subproblems. Maintain scripts to log run metadata like date, device, calibration metrics, circuit version, so on and so forth, so you can actually compare results over time as hardware evolves. Engaging early with platform communities like forums, user groups, helps also learn better practices and avoid pitfalls, because I myself have been engaging in user groups for quite some time and I learned quite a lot than just using regular documentation. Over time, this actually helps build reliable experimentation pipeline. So now actually, how do we do software and algorithmic development? Developing quantum applications involves more than writing circuits. First, translate a business problem into quantum-friendly formulation. For optimization, define cost functions and constraints that fit variational algorithms or Ising model mappings. In a finance pilot, a team had to express expected return risk covariance as cost Hamiltonian, translating domain concepts into qubit interactions. Next, optimize circuits for hardware. Choose qubit mappings respecting connectivity, decompose gates into native operations and limit depth to stay within coherence times. It's like customizing a recipe for available kitchen tools, right? You might want to swap an ingredient here and there and adjust the cooking time based on the stove. During the execution, apply error mitigation. Run circuits at varied noise levels, correct measurement statistics, and extrapolate towards ideal results. I remember running the same circuit with doubled gate durations to amplify noise, then using extrapolation to estimate the zero noise output. Though imperfect, it gave a clearer signal. Post-processing integrates quantum outputs into classical decision pipelines, feeding refined solution into larger workflows. Iteration is key, basically. Simulate with realistic noise models, adjust circuits, run hardware tests, analyze deviations, tweak again. Over time, teams develop intuition. You get to know this over time. And version controls matter. Keep circuits in repositories, tag versions, track transpilation settings. Avoid simulator tests to catch regressions. Automate simulator tests to catch regressions. Log results systematically so that you actually get to know what is really going on. You can compare tests over time and so on and so forth. Next, what goes on with the organizational strategy? A structured approach maximizes impact. First, identify use cases with clear metrics and manageable scope. Host workshops where domain experts outline pain points, then assess which might suit quantum pilots. For example, a retail team might point to seasonal inventory imbalances, a logistic group flags dynamic routing challenges. Second, build capability. Train staff through online courses, internal hackathons, or partnerships with research labs, so on and so forth. Form small quantum skunk work teams empowered to prototype ideas quickly. Third, execute proof of concept experiments, run on simulators, then hardware. Define success criteria such as solution quality improvement over time, savings relative to classical baselines. In one organization, they set a threshold. If a quantum pilot could match classical results within 5% of error, they considered it worthwhile stepping stone. Even matching performance builds familiarity. You get to understand the quantum landscape. So allocate budget for cloud compute over time, maintain a roadmap that revisits use cases as hardware matures, avoid ad hoc experiments with no clear business alignment. You would definitely want to focus on measurable outcomes and learning objectives. I have seen companies spend months running random circuits without tying them to specific problems. They end up with reports full of technical jargon but little business insight. In contrast, teams aligning pilots to concrete use cases actually do better. So, what is the near time? What is the future of the quantum business value? Even in NISC, teams report modest but meaningful improvements, faster optimization on scale on small to medium instances. I might shave a few percentage of delivery times. A chemistry experiment might rule out a false read early. Finance test might tighten risk securities. What starts as a pilot on a reduced small scale model becomes a full scale application later. The experience gained, understanding noise mitigation, hybrid design, platform quirks become priceless when fault tolerant machines arrive. So, by balancing realistic expectations with curiosity and experimentation, you actually understand how to harness quantum breakthroughs as soon as they become practical. In my experience, teams that document every pilot, success or failure, built a knowledge base that later accelerated their work when improving devices reach sufficient scale. What once was a dozen qubit experiment becomes a stepping stone to hundreds of qubits with minimal fraction. What are the key takeaways, right? Quantum computing in today's NISC era is not a magic bullet, but if it offers genuine opportunities when we choose suitable problems, adopt hybrid methods, and building internal capability is dividends as hardware improves. I encourage you to identify one well-scoped use case in your domain, perhaps a small optimization or a simulation that fills tens of qubits and shallow circuits. Run a pilot on simulators first, refine your formulation, test circuit designs, then move to hardware runs, collecting data, document literally every step, share all your lessons across teams, engage with the wider quantum community. Over time, you will build a repository of patterns, common ways to map problems to variation circuits. These patterns reduce friction for future projects, allocate a mod, and how encourage a culture of exploration balanced with pragmatism. Celebrate small wins, which will definitely help you set the groundwork. Embrace this era of exploration with both enthusiasm and pragmatism. Thank you for listening. I look forward to your questions and your continued conversations about how quantum can actually create value in your organizations. Thank you again for joining Conf42. Hope you all have a good time.